So yesterday we talked about the electromagnetic wave propagating in a conducting medium, and when it propagates through a conducting medium, it is observed that this is how it is. Electric field component of that electromagnetic wave is represented, and we can see that amplitude of this wave, which depends on x, it is x dependent amplitude, and this decays exponentially with distance moved through the medium. So it is E naught times e raised to the power minus beta. Beta is coefficient which is called attenuation constant or attenuation coefficient, absorption coefficient as well. So it varies, or you can say amplitude that varies with x as this exponential function, and we see that it for x equals to 1 by beta, the amplitude becomes E naught divided by E. So that is defined as skin depth or penetration depth for given or electromagnetic wave in the given medium. So this is, and there is no change in amplitude as we saw in case of free space when there is no a material medium, it is vacuum, then there is no attenuation of the wave and amplitude remains same. Then next is electromagnetic wave. it, किसी का अनम्यूट हो गया बेटा माइक, check your mic. Okay. Then we have as this electromagnetic wave, whenever electromagnetic wave it propagates, it carries with it energy and momentum. So energy it carries with it. We want to define that, and it is defined in terms of Poynting vector. And we exactly Poynting vector is what? It is energy that propagates with an electromagnetic wave per unit area per unit time. If electromagnetic wave is incident on any surface, then Poynting vector means what? It is energy incident normally on unit area of the surface per unit time. That is what? That is Poynting vector for electromagnetic wave. So these are electromagnetic waves. You can see this electromagnetic wave is what it is. It is a traveling electromagnetic wave. Energy, it is carrying energy as well as momentum. So energy that flows through this electromagnetic wave per unit area per unit time is Poynting vector. So the amount of power is energy per unit time. So it is amount of power per unit area, means units will be watt per meter square carried by electromagnetic wave in free space is given by Poynting vector. And Poynting vector is, you can see here mathematically it is defined as S vector as cross product of E field component of electromagnetic wave cross product of this with B field component of electromagnetic wave divided by permeability of the space. Here it is free space, so it is what? It is permeability of free space. Or we can also write it in terms of H, because mu B divided by mu naught is what? It is H, so it is E cross H. And direction of this, magnitude of this vector is what? It is magnitude of this cross product, and direction is perpendicular to both, that is E and H, because it is cross product of E and H. And we can find direction, and direction is same as that of the propagation of electromagnetic wave. If this is Y component of electric field and this is Z component, then we can say that this cross product will give you direction of Poynting vector, which is along X direction, positive X direction. Okay, so we have Poynting vector, which gives you idea about amount of energy carried by electromagnetic wave. Exactly, it is energy per unit area per unit time. It is a vector quantity. Direction of this vector is same as that of the propagation of electromagnetic wave. If electromagnetic wave is propagating in x direction, then Poynting vector direction is also x. If it is in y direction, we consider electromagnetic wave propagating in y, then direction is what it is y. Straight away, we said that it is formula is given as cross product of E and H, or it is in terms of B, magnetic field induction. It is E cross B divided by mu naught. Let us see from where we get this formula. From basic definition of Poynting vector, we can derive that it is what it is cross product of E and H. And basic definition of Poynting vector is what it is: energy per unit area per unit time. So let me say that electromagnetic wave is propagating along x direction, and with it, it is carrying energy due to E field as well as due to magnetic field B. So as there are two components of electromagnetic wave, so energy due to E field plus energy due to B field will make what energy is propagating this with this electromagnetic wave. So for that, let me write U subscript E. This is energy density. Units joule per meter cube. I'm talking about energy per unit volume now. So energy per unit volume due to E field component of electromagnetic wave is what it is: half epsilon naught E square. You are familiar with this expression. You have derived this expression in your lower classes for energy density between capacitor plates. Charging discharging हो रहा है, तो we say that charge grows on the plates, and then electric field varies, and then energy density, energy per unit volume between the plates of the capacitor is what it is: half epsilon naught E square, where epsilon naught is permittivity of free space and E is electric field. Similarly, we can write, and for H component or for B component of electromagnetic wave, we can write energy density associated with B field of electromagnetic wave is given by, it is B square divided by 2 mu naught. This also you can derive. Solenoid may have seen, we can derive energy density, and it is given by this. So that means total energy density associated with both the components, which energy, this is the energy which is carried by electromagnetic wave per unit volume. This is sum of these two energy densities. It is half epsilon naught E square plus we have half B square divided by mu naught. We know relation between electric field, magnitude of electric field and magnitude of magnetic field, and this relation is well-known relation. We know that E is C times B. What this means, that this E is magnitude of C is C times E is C times bigger than magnitude of B, and using this relation, or I can write that B is E divided by C, or B square, which is E square divided by C square. So I can replace this B square by E square over C square. So total energy density for electromagnetic wave is sum of these two terms plus I have half, let me write mu naught as well, and this is B square, which is E square divided by C square. And we also know from our previous understanding that 1 over, let me write directly, 1 over C square is mu naught. It is mu naught epsilon naught. So let me use this as well here. So I can write total energy density is half epsilon naught E square plus this is 1 by 2 mu naught with c square as well. I have c square or c square I can use. I know what is c square. So let me use that c square, which is mu naught 1 over c square, which is mu naught epsilon naught, and I have e square here. So mu naught gets cancelled with mu naught. I'm left with half epsilon naught E square. This is energy density due to electric field component of electromagnetic wave, and this is energy density due to B field component, and both are equal. We can also conclude from here that energy associated with electric field component, energy density, is exactly equal to energy density associated with B component of electromagnetic wave, whereas their amplitudes are not equal. Amplitude of electric field is C times the amplitude of magnetic field. But energy associated with these fields are equal, energy densities are equal in propagating electromagnetic wave. So I can write that total energy density is epsilon naught times E square. So half epsilon naught E square times half epsilon naught E square gives you this. This is when electromagnetic wave is propagating. So per unit volume, you can choose any unit volume, and you see that if electromagnetic wave flows through that area or through that volume, then energy density or energy carried by that unit area, unit volume is what it is, epsilon naught E square. This is in joule per meter cube. I'm interested in what? I'm interested in writing Poynting vector. I have idea how much energy is carried or how much energy is there in unit volume, but I want to convert this, or from this I want to write what is energy flowing through unit area in unit time. So how much energy flows through unit area? If I choose a unit area, this is my unit area, 1 meter square area, and electromagnetic wave is incident on this unit area. So how much energy flows through this unit area in 1 second time? That is my Poynting vector. So I'm interested in writing that Poynting vector. So for that, let me do two. There are two different ways of doing it, or you can do it by. Let me do it by this way. So I have what I choose a small region in the space through which electromagnetic wave is propagating, and that region is a region between these two, let me say, parallel rectangular plates. Area of each plate is what it is A, and separation between these two plates, or you can say electromagnetic wave, it moves from this to this plate in time delta t. Delta t is the time taken by electromagnetic wave to move from this plate to this plate. So this region between these two plates, I can find volume of this region. So volume of this region between two plates is what it is, area of cross section, that is this area times distance between the two plates, and distance is not known, but I know what I know, time taken by electromagnetic wave to move from one plate to the other plate is what it is, delta t. And speed of electromagnetic wave in free space, this we are doing for free space. So it is c times delta t is separation between these two plates. So time taken into velocity of electromagnetic waves, this is separation. So I can write that volume of this region जिसके बीच में हम electromagnetic wave को देखना चाह रहे हैं. So volume is what it is, area times area of each plate times separation between two plates. This is volume between these two plates. And energy density is given to us, and we know that energy density associated with electromagnetic waves is energy density, not with E, it is with total. Let me write total energy density with both the fields, that is E as well as B. I can write total energy density is epsilon naught E square. So this is energy per unit volume, and this is volume between these two plates. So what is total energy between energy of electromagnetic waves between these two plates? That total energy I can by multiplying these two, I can write capital U. This is small u for energy density, and this is capital U for total energy in V volume. So I can write it is energy density times total volume. So it is energy density, energy per unit volume times volume. Total volume is A times C delta T. What is this? This is total energy in this region. जो हमने select किया space में small region, or you not small region, we have selected a finite region in the space. And in this region, what is the energy, total energy due to electromagnetic wave? It is given by this, and we are interested in total energy or energy propagating through unit area in unit time. So I can say that this is the area through which this electromagnetic wave will propagate. It will flow like this. Whole of the energy within this region that will flow out from this region through this A area. So I can write that energy flowing through A area in delta t time, and because I know that time taken by electromagnetic wave to propagate from this plate to this is what it is, delta t. So in delta t, whatever energy is there between these two plates, that will flow through A area. So what is the time? It is delta t, in which this whole energy will flow through and area is what? A. So I have to make both one, or you can say that I divide this total energy divided by area divided by delta t. This gives me what? This gives me this total energy propagating through unit area in unit time. Okay, this is flowing through A area in delta t time. So I have divided that by A and delta t to get what energy flowing through unit area and unit time, which is equals to epsilon naught E square. This is total energy A C delta t. This is total energy divided by A times delta t, and I can cancel A with A, I can cancel T with T. So I'm left with what? I'm left with epsilon naught. The C is also there. So let me write C epsilon naught E square. What is this? This is Poynting vector. This is energy flowing through unit area in unit time. Okay, and because we defined Poynting vector mathematically, we said that Poynting vector is what it is, cross product of E and H, or we said it can also be written as cross product of E and B with mu naught in the denominator. So I want to see this as this expression. So for that, I have to make little changes here. So some changes, if we make, it will look like this expression. So it is C epsilon naught. I can write this E square as E times E. Okay, E times E. And this E times E, we can at the same time we can use that E is what it is. It is. Let me erase this first. Okay. So I know that this is C epsilon naught E times E, and one of the E for one of the E fields, I can use this relation, that it is C times B, or the C times C will give you C square. It is epsilon naught E times B, and again using this relation here, I can use this. C square is 1 over under root, or C square is 1 over mu naught epsilon naught. So let me write it as epsilon naught. It is E B divided by mu naught epsilon naught. I can cancel this with this. So magnitude of Pointing vector, it is E times B over mu naught, or you can write this is equivalent to what? It is equivalent to, in place of this, if I write H, so I can write it as this. And in vector form, you have to write this as cross product of two vectors, and cross product, order of the cross product for that, as we said, that direction is same as that of the propagation of electromagnetic wave. So to get that direction, we write it as E cross H. If I write H cross E, then you will get what direction opposite to the propagation of electromagnetic wave. You can see this. So Pointing vector is magnitude of Pointing vector. It gives you energy propagating per unit area per unit time. So whenever electromagnetic wave it propagates in the medium, then through unit area, what energy will flow through in one or unit time, that is what that is Pointing vector. So we started with the basic definition. Initial steps we did to write energy density, and then we selected a region where we said that total volume of that region is A times this, and then we said that energy density times that total volume will give you total energy in that region, and whatever energy is contained by this region that flows out through this A area in delta T time. So dividing that total energy by A and delta T, that gives you what flows through unit area in unit time. And this is definition of Pointing vector. And then doing small modifications by writing, because I want to write not only in terms of E. This is also Pointing vector. This is expression for Pointing vector. I want to write it in terms of both the fields E as well as B. So one of the E can be written in terms of B using this formula, and then you get what you get. And you can write many other relations for by converting E into B and by converting H into B and many more. So this is expression for Pointing vector. This was derived using this picture. Even we can derive it by saying that let us choose a big figure, parallelepiped figure. Area of cross section of that is 1 meter square. So we are पहले से हम 1 meter square लेके चलते हैं, and we say that let us say that it is a big parallelepiped figure, and separation between these two 1 meter square areas is what it is. It is equals to C. Okay, so this distance will be traveled by light in 1 second. So I'm fixing where I said that delta T is the time taken by electromagnetic wave to move from one plate to the other plate. Here we are saying that separation between two plates is such that electromagnetic wave goes from one plate to the other plate in 1 second. So you have to make this distance equals to 3 into 10 raised to the power 8 meter per second. So that's why. So then you can see whatever energy flows through this. You can try the alternate way of deriving this. Okay, so you get what simply by knowing what is the energy density and what is the volume of this parallelopipe. By multiplying those two, we get whatever, because now area is 1 meter square. I need not to divide by A. I need not to divide by delta T, because I have chosen delta T in such a way that it is already 1 second. So you can again write the same expression here. This is Pointing vector. Okay, so now we know how much energy is propagating through this electromagnetic wave, and we know that electromagnetic wave, it carries with it energy as well as momentum. Momentum due to if we see photon picture, we say that electromagnetic waves are like what they can be imagined as photons of momentum of each photon is h nu divided by c, given by Einstein. Einstein said that electromagnetic wave or light is like what it is. It is having wave as well as particle characteristic. Due to its particle characteristic, it is like shower of these small photons, and each photon having energy h nu, and momentum of these particles, photons, is h nu divided by c. Okay, so this is what was proposed by Einstein, photon picture of light. So due to this momentum of photon, whenever these photons or this light is incident on any material medium or on any object, there will be transfer of momentum from photons to that object, due to which when photon is absorbed by any body, that means momentum of the photon is absorbed or momentum is transferred to that body, and that body will experience pressure or force which is called radiation pressure. So we'll talk about this radiation pressure more uh, in a time. So उससे भी पहले important is what it is. This is electric field. We are saying that Poynting vector, it is 1 over mu naught times E cross B, where E is electric field, B is magnetic field, and this E is what it is, function of R and T. It varies with what? It varies with R, that is position in the space, and T. So it is, this value is what it is sinusoidally varying with time. And this B is also what it is sinusoidally varying with time. Maximum value of E is called amplitude, that is E naught, and maximum value of B when electromagnetic wave propagates, maximum value of B is what it is. So it varies from 0, then it goes to E naught, then again 0, then so this is how E oscillates with time. Similarly, B oscillates with time. Okay, so their values are not always E naught and B naught at all times, but it is what? It varies from 0 to maximum. So we can write it as sine omega t, and this is B, which is also proportional to sine omega t. So in this, we'll be having what? Product of sine omega t and sine omega t. So we can say that S dependence on time is what it is, square of omega, sine square of omega t. And as I said that this varies from 0 to its maximum value, this also varies from 0 to its maximum value. So to know what is the average of, okay, this is what this is, average of sine over its time period. This is sine, but it is sine square. So sine square is this. So average is what it is, half. It varies from 0 to 1, 0 to 1, and average is what it is, half. So we can write that average, if I replace this by E naught and this by B naught here, so what you are getting is, you are getting maximum value of Poynting vector. Maximum energy flowing through unit area and unit time. It is when we choose E as E naught and B as B naught. As you know that they are not fixed, they vary sinusoidally with time. So that's why we take time average over the time period, and then we say that this is the expression for Poynting vector in terms of E naught and B naught. Okay, so it is then half is multiplied here. So this is due to average values, and using this we can do numericals related to this are like, if electric field and amplitude of electric field is given, if electromagnetic wave is propagating, and for that electromagnetic wave, E field amplitude is 100 volt per meter, then by simply replacing this by 100 volt, and then you see what you get, mu naught and C are constants, and then it gives you 13 watt per meter square. Okay, this is Poynting vector. This much energy will flow through unit area in unit time, or you can say this will flow through you, because your area is roughly our body area is 1 meter square, roughly. So this much power, this much energy will flow, joules per second. You can say 13 joules per second. This much energy will flow through you in 1 second. Okay, or 13 watt power will flow through you, through your body. This is when electromagnetic waves. This is when the electromagnetic waves incident on your body have E field having amplitude equals to 100 volt per meter. ओके, बट एक्चुअल में क्या होता है? एक्चुअल में जो सन रेडिएट कर रहा है इलेक्ट्रोमैग्नेटिक रेडिएशंस, amplitude of E field in that is 1000 volt per meter, and this produces 1000 times more because it is 1.3 k kilovolt per meter square is the pointing vector what sun is radiating, and this is to fry our body. But again, what is the concept? We are choosing E naught, but it is not E naught, it is average, and we say that it is not always perpendicular. This is when we say that this comes when electromagnetic wave is perpendicular to the surface. Okay, so otherwise it is what it is not perpendicular, then this component you have to find. It is making some theta angle with the normal. Then you have to find the component of that electromagnetic wave, and then it gets reduced. So that's why it is not that harmful. Then we have sun is radiating this much of power every second. Energy propagated in joules is 3 into 10 raised to the power 26 joule per second is the energy radiated by sun, and distance between sun and earth is what it is, this much kilometers, 150 into 10 raised to the power 6 kilometers. Then we can see what power or what is the energy that is incident on earth per unit area per unit time due to this what sun is radiating. So you can simply do the calculations. You see that it radiates in all directions, energy is distributed in all directions, and this is the sphere you can draw equal to distance between the sun and the earth. So this energy is incident on this, it is radiating this per second, and it is incident on this area of this sphere. So by dividing this, that is energy total, it is 10 raised to the power 26 watt divided by area of this sphere. So you can write 4 pi into 4 pi r square, that is this much, and you get what is the Poynting vector, what energy per unit area per unit time or Poynting vector related to this. Okay. We have another concept, as I said, that energy is carried by electromagnetic waves. It carries energy as well as momentum, and momentum is due to, you see photon picture, so it carries energy. Each photon carries energy this, and each photon carries momentum h nu divided by c. So this is what this is momentum carried by each packet of energy, and this gives this, when it is absorbed by any body, it transfers its momentum. Photon will transfer its momentum to that body, and which results in what it results in, which is very you can say small. You do not experience that pressure, you do not experience that force, but in some cases this has significant effect, and we can observe that, and we can see effect of radiation pressure. So we say that it is radiation pressure is exactly what it is, S divided by C. S is Poynting vector divided by C, which we can write it as energy divided by energy. S is what it is, energy per unit area per unit time. With this we have C here, and energy divided by C, as we see energy divided by C is what it is, momentum. So this is the momentum of photon, and momentum divided by, you can write this as momentum divided by meter square area and time in seconds, and momentum divided by time, momentum divided by time is what it is, force. So I can replace this by force. This is force, and then we have what it is, force divided by meter square or divided by area, which is pressure. So this has units of pressure. So this S divided by Poynting vector divided by C gives you radiation pressure, and with this we have another parameter, this is alpha. So exactly radiation pressure exerted by electromagnetic waves on any material or any body, that is decided by this, that is S divided by C times alpha. This is dimensionless parameter, and it is different for different bodies. It depends on how body interacts with electromagnetic wave. So if alpha is 1, that means full absorption. Okay, alpha 1 corresponds to full absorption, and in that case, S divided by C is the radiation pressure. Okay, and if alpha is 0, no absorption, means alpha 0 and there is no radiation pressure. Why? Because alpha 0 makes it, there is no absorption, or you can say that light propagates or travels through the material medium without any change in momentum. So no momentum is transferred from body to the material medium. In that case, that is called no absorption, means alpha is 0, and then radiation pressure is also 0. And if alpha is 2, that means 100% reflection. Body is reflecting electromagnetic waves. Why alpha 2? Because then moment transfer of momentum is twice. Okay, change in momentum is this. So uh, this is the change in momentum, which is 2p, and due to this radiation pressure is what it is. It is twice of the this S by C. So this is how, and where it is significant, as I said, that in case of comets में जो tail होता है, comet जब sun के नजदीक जाता है due to gravitational force, we see that यहाँ जो radiation emit कर रहा है sun, इसका जो tail है, which is made up of dust particles and some carbon dioxide gas and some gases. So you see two tails of the comet. First is blue tail of the comet, और एक आपको white tail दिखाई देता है. Blue tail is due to what? It is due to excitation and de-excitation of these gas molecules, and when they get de-excited, they emit light in this region of electromagnetic spectrum. And white light is due to what? It is due to electromagnetic waves are reflected back and by these dust particles, and you see white light, and you can see what you can see. ये जो tail है, ये radiation pressure की वजह से that tail you can see in case of comets. So this is where we can see that it is significant radiation pressure. Let us talk more about electromagnetic waves. Electromagnetic waves are traveling, and electromagnetic waves are produced due to oscillating, accelerating charges. When charge accelerates or it oscillates, it produces electromagnetic wave. And wave equations, which we derived using Maxwell's equations for free space, these are for free space because epsilon naught, mu naught are involved here. And these are wave equations for electromagnetic wave traveling in any direction, infinite number of directions. And you see that here E is function of R and T. R is a position vector which can be drawn anywhere in the space. So that will be the direction of propagation of the electromagnetic wave. But to keep our things simple, we talk about one-dimensional case, or the case where direction of propagation is only one. So if we say that electromagnetic waves are propagating along x direction, in that case, there will be only one solution for this, and one of the solution which we can write for this E field, it is what it is. Let us say that direction of propagation is x. So in that case, I say that electric field is along y direction, and it is varying with, this is the direction of propagation with t, x and t, and it is j cap, direction is j cap, and this is equals to amplitude of this field, electromagnetic E component of electromagnetic wave. And this is sinusoidally, it varies with x and t, so it is what it is, kx. So I can write solution for the b or h, whatever you write it as. B is equals to, you can say b is in z direction, when direction of propagation, and this is what, this is k cap, showing direction of this vector. It is, and this is equals to b. This is amplitude in z direction, amplitude of b. This is cos. It is propagating along positive direction of x-axis. So you can write this as, sorry, this is k cap here, and this is k cap. Okay, when positive x is the direction of propagation. So we can write solution, this and this for propagating electromagnetic wave. Okay, and we know that from Maxwell's equation, these are related by Maxwell's equation 3 by like this. It is E del cross E is equals to negative of d by dt of B vector. Okay, we are, if you see what I mean by this is electromagnetic wave propagating in this direction, that is positive x direction, and this is my y direction. In this direction I have E field. It is sinusoidally varying with x as well as with t, and I have this as z direction, and in this direction I have B component of electromagnetic wave. This is also varying sinusoidally with time and x. Okay, and this is what, this is your E naught, and this is amplitude, this is B naught, amplitude of B field. Okay, so there are no other components. If I write E field, which is you can say, or let me write it in that form. E field is what it is. E x component of E field. Let me say I cap. I can write plus j cap, and it will be it is having all the components. It is this k cap. It is Ez. And similarly, you can write B field as having all the components. B is I cap Bx plus j cap By plus k cap Bz. This is not for this electromagnetic wave. This is for electromagnetic wave which is propagating in all possible directions. Okay, so using this relation, I can find curl of E. Curl of E is then determinant. It is given by determinant. It is unit vectors I, j, k. This is curly components of this del operator. These are components, x, y, z components. I can write electric field components, Ex, Ey, and Ez. And then you find this determinant, which gives you components of this, that is del cross E. So this is I component of del cross E, which is this minus this, plus you can write j cap, and it is curly over curly x of Ez minus curly over curly z of E. With opposite sign, let me write it as z. This is x, and this is x, and this is z. Okay, plus you can write other component, that is z component here. Okay, and now you can write this side. This is d by dt of Bx I cap plus j cap By plus k cap Bz, equating these two, this and this. We see that we can equate them, and we can see for our electromagnetic wave, we have to write only what we will be having this z component. These two components are not there. I have magnetic field along z component. So I'll compare it with z component of electric field. So you can write that it is this is equals to minus negative of d by dt when I'll operate with this operator on this. So this will give you what it will give you. dt here, and this is z. So this is what, this is my wave equation, or you can say this is what, this is a relation between these components. And if I substitute these solutions, these solutions in my here in this equation, it should satisfy, because all the components, E and P components, should satisfy this. That is Maxwell's equation, third equation. So if I differentiate this EY component, this is EY with respect to X, then EY with respect to EX with respect to, this is not there, it is 0, there is no EX component. And I have differentiated this B Z with respect to BZ with respect to T, and then equating, you see what you get. Derivative of EY with respect to X, this is my EY, and its derivative with respect to X gives you what it will give you. It will give you, yes, it is K E naught. It will be sine with negative sign. It is sine K X minus omega T. Okay, and then d by dt of Bz will give you what? It will give you derivative of this with respect to T, and derivative of this with respect to T is omega B naught. This is sine Kx minus omega T. Okay, sine cos ka derivative sine with negative sign, and but this minus omega T is also there, so it makes it positive. So you can say that this is equals to this, and with one more negative sign, that is this negative sign makes it negative. So then this is gets cancelled with this. Sine gets cancelled with sine. So I have relation between E naught and omega. So I can write that this is what, this is omega is equals to E naught divided by B naught. Omega, not omega only, omega divided by K. Okay, this is what, this is K is also there. So you can write that it is omega divided by K. And omega divided by K is what? It is velocity of propagation, as it is free space here. So we can write it as 2 pi nu divided by 2 pi over lambda. K is 2 pi over lambda. 2 pi gets cancelled with 2 pi. It is nu times lambda, which is in case of free space, it is C. So we can say that B naught divided by, sorry, E naught divided by B naught is what it is, C. This is how their amplitudes are related. So E naught is equals to C times B naught. It is not amplitudes, magnitudes of E and B. This is the relation that E is always bigger than B, and E is C times bigger than amplitude of C is, sorry, E is C times bigger than amplitude of B. Whereas energy density is associated with both E and B are equal. They are equal. E and B they are perpendicular. Okay, so dot product of E and B should be equal to 0. They are orthogonal vectors E and B. So you can see that, and we derive that C is under root, or C is 1 divided by root mu naught epsilon naught. So with this, we can say that we can go for these are traveling electromagnetic waves. Okay, electromagnetic waves are propagating. There is time dependence, there is space dependence, and both they are varying sinusoidally. You can fix one, and you can see dependence on the other parameter. You can fix position, and then you see how it depends on time. You can see sinusoidal variation. If I fix time and I see dependence of field, any of these two fields with X, again you will see that sinusoidal variation is there. So these are propagating electromagnetic waves. Then we can also write standing electromagnetic waves. When we have two electromagnetic waves traveling in opposite directions, they superimpose, then a resultant of that is what it is. It is an electromagnetic wave, or it is a standing electromagnetic wave. So for that, you have to write, this is, you can say E1, this is electromagnetic wave propagating in positive X direction, and electric field component of that electromagnetic wave, which is along y direction, is what it is, E1y. It is representing wave 1. This is for wave 1, which is propagating in this direction. It is positive x direction. Then you'll be writing E and B components, electric field and magnetic field components for this wave, which is propagating in negative x direction. So we are focusing on 1, then we'll see how we can write E and B fields for this electromagnetic wave, which is propagating in negative x direction. So you write what you write, amplitude of this field. It is sinusoidally, it varies with both. These are traveling waves. So it varies with omega t and as with t as well as with x, and k1 and omega 1 are wave vector and angular velocity of this wave 1. I can write it as k1 x minus omega 1 t. Okay, similarly, you can also write magnetic field component or magnetic field associated with this wave. This is B1z. Magnetic field is perpendicular to both direction of propagation as well as the direction of E. So as E is along y direction and it is propagating in x direction, so I can write that it is Bz, and amplitude of this is B10, and it is, again, there is no phase difference between this and this, so phase remains the same. Now for ray 2, it is propagating in negative direction, so I write this is 2. I can write amplitude. This is 0, 2. Let me say that it is 2. It is cos k2 is the wave vector associated with this wave minus omega 2 t. As it is propagating in negative direction, I should write minus k1 k2x, and negative I can take common. It is cos minus theta, which is cos theta, so no need to change sign here. And you can write B2z, that is B component of this electromagnetic wave. It is B20. Again, using the same logic, I can write it as cos k2x plus omega 2t. With this, we have to keep in our mind that E cross B should always give you direction of propagation of electromagnetic wave. It is in first case, this is positive direction, and here E cross B is not giving you positive direction of X propagation. So it is with negative sign I should write here. So now it will be what? This cross this will give you negative direction of propagation of electromagnetic wave. Okay, so with these changes of these are two electromagnetic waves. These equations are representing two electromagnetic waves, one propagating in positive direction of x-axis, other propagating in the negative direction of x-axis. Let us say that they superimpose. So by simply adding these two, we can say that there is superposition of these two waves, then standing wave is formed. And we can say, for our convenience, let us say that amplitudes of both the fields for both waves propagating in positive, negative directions are same. So these amplitudes are same. Amplitude of B field is also same for both the waves. K1 and K2 are also equals to K. Omega 1 is equals to omega 2, and that is equals to omega. So with these, I can conveniently write these equations, and then I can write the resultant electric field of standing electromagnetic wave EY. This is what it is, resultant of these two. So I can take, because now both are E naught, so I can take E naught common, and you can write this as cos. This K1 is K, so it is Kx minus omega t Okay, and then this is minus cos kx plus omega t. So this is superposition of electric field components of two oppositely propagating electromagnetic waves. And you can similarly write what you can write resultant magnetic field due to superposition of two waves traveling in opposite directions. Then it is what it is, superposition of these two, that gives you B naught is same for both the amplitude of both the waves, and then it is cos kx minus omega t, then this, that is plus cos kx plus omega t. Okay, so and we can use our trigonometric knowledge to write what that cos a plus b or plus minus b is equals to cos a cos b minus plus sin a sin b. So using this relation everywhere here, because I have all the cos terms, cos, sometimes I have cos kx plus omega t, and sometimes you are having cos kx plus omega t. So using these, I can write that Ey is equals to, this is E naught, and this cos a minus b formula, if I use, I can write it as cos kx cos omega t. It is plus sin kx sin omega t minus, let me use this formula, cos a plus b. So it is cos a, that is kx, cos omega t minus, but this is also negative, so negative makes it plus, it is sin kx sin omega t. So this gives, let us see, this gets, no, sorry, this gets cancelled with this. So I'm left with 2, this is E naught, 2 E naught sin kx sin omega t. What this is representing? This is representing E field associated with standing electromagnetic wave. This is E field component of standing electromagnetic wave. It varies sinusoidally with x, it varies sinusoidally with time. Similarly, you can write, if you solve this, you can write B field component of standing electromagnetic wave, that is 2 times B naught, it is cos kx cos omega t. So these are standing, these equations are representing standing wave, electromagnetic wave, and E and B components of standing electromagnetic wave. We'll go into more details. We'll see where are the nodal planes and where are the antinodal planes for E field and above B field, and what is the phase relationship. It is important because we said that in traveling electromagnetic wave, E and B are always in phase. Okay, and in standing electromagnetic wave, we'll see what is phase difference or phase relationship between E and B, and then we'll see that the spatial dependence. We'll see that how E and B fields they vary with x, and how E and B fields they vary with time t. And in this light, we can write Poynting vector for both traveling electromagnetic wave and Poynting vector for stationary standing electromagnetic waves. As well as we can write energy density for traveling electromagnetic waves, and energy density associated with these standing electromagnetic waves. So this is what we'll be doing in coming lectures. Let us stop here only. It's time. If you have anything, there is rigorous